we can start, I guess, before. All right, let's get started. So this is our last seminar of the year. And to wrap it all up, Brett is going to present, and my phone will wake up. Brett Robbins received his BSEE and MSEE from the University of Illinois at Urbana-Champaign and is currently pursuing his PhD. His research is focused on the distributed control and optimization of power systems. In addition to engineering, he has earned vocational certificates in automotive repair and refinishing and welding.
Thank you, Saming. Sounds just as good as the last time, back in October. So you can see here I picked a very generic title, very broad, just because Alejandro called me a week ago and he's like, "You want to present?" And I'm like, "Sure." So I just sent out something that was a catch-all. And so really what this is going to do is it's going to build upon the work that I did over the summer through NAPS, a journal paper that we have out while we're wrapping up. And so I'm going to make a lot of assumptions that you actually kind of remember what I talked about last time. But I'm going to try to lay enough background, and if you really want to know the details, talk to me later. Just to kind of start out with a little bit of motivation, I say here that distribution systems are undergoing significant transformations in structure and functionality. This has to do with advanced communication, sensing, and control. These are things we get very excited about as engineers. We're incorporating variable generation. This could be PV, as well as storage-capable loads, which are going to be like plug-in electric hybrid vehicles, or the Teslas, which would be really nice. This is a pretty exciting time to be an engineer, because not only do we get to figure out how to do this stuff or even come up with these new ideas, we also have to address all the problems they create. And so we have a lot of challenges that we have to deal with here. And so, for example, let's look at PV generation. This is very dependent on the sun. I've seen a lot of installations on houses where there are times of days where you actually generate a lot more power than you consume, and maybe you even have a net generation overall for the week. But the problem is, not only does it come at an inconvenient time of the day relative to the load, but then it can be very variable if we have cloud cover. And I found this stat here that says it can ramp up on the order of 15% of its capacity per minute, which as power system operators, we don't really like that kind of variation. The other problem we run into is that if everybody in the neighborhood puts PV panels on their houses, we run into voltage rise as well as a reversal of active power. So rather, if we're looking at this distribution system, rather than the power going into it, it's coming out of it. The other thing that is of interest is that if you have a Tesla or a plug-in electric hybrid vehicle where you're running on electricity all day, when you come home at 5, the first thing you're going to do, assuming your battery's low, is just plug it in. So we have these issues with the load because the load is already historically high that time of day. Most of the generation we set up for reserves and everything is associated with that peak, not that we actually need it throughout the day. And the other thing is, as we add this variability, our traditional components, which are going to be like capacitors or voltage regulators, which are transformers where we can change the taps, this is going to introduce additional wear on the mechanical parts. And so we'd like to avoid that because it'll shorten their lifetimes. And so I'm going to talk about our control, and then we're going to switch into the bulk of the presentation, which is going to be the slow time scale, which is what I presented last semester, but this is actually the distributed results for it rather than just the centralized. And then I'm going to have one quick like token slide about current work at the very end. And so the motivation, we can kind of, if we take a snapshot of like a radial feed that you can see here, and this is slightly exaggerated. And so intuitively, all I did is I created a radial feed and I put loads everywhere. We have this voltage profile here. And so if we have a transformer, let's say halfway through, we correct our voltage in the following way.
It's just a line, the graph is just a line.
Yeah, it's just a line. This was just purely so you can conceptualize it. And it's pretty exaggerated too. Like this would be a bad design. So if we include a transformer partway through, we can affect all the voltages downstream of it pretty significantly. And then the idea with reactive power support, in particular the distributed energy resources, which are going to be anything with power electronics, we take that to kind of shape it even more so, because we can only do so much with one transformer. So we can raise the voltages at the end here. And this can be based on some sort of objective function, whether or not you're trying to track 1 per unit or whatever. So kind of just keep this in mind. And so the way we look at this when we want to control it from like, so if this is a snapshot, think of it like, if I start this morning, how is it going to run throughout the day? And so I was telling you earlier, like, we don't actually want our transformers to react all the time. And so the idea is we're going to classify those as slow time scale control. And we're going to periodically dispatch that. And then in between those points, we're going to be doing reactive power support through various means. And so what we do is we envision a hierarchical approach that uses time scale separation. And then, like I was saying, we classify as slow time scale and fast time scale. This is going to be conventional devices, such as transformers, because we don't want those moving all the time. It could even be capacitors, because usually those don't have much granularity in terms of how much capacitance we add, and then a lot of times they'll switch them based on seasonal data. And then we also have our fast time scale. And like I said, this is going to be like the distributed energy resources or the dynamic response resources. So this is anything really with power electronics that are switching anyways, so we can control the phase. And so the next few slides, I'm just going to burn right through these. These are more of the review, and this has to do a lot more with notation than I necessarily care if you understand all the assumptions I make. And so take this transformer right here. We're going to say this is an ideal transformer where we can control the ratio, right? And we're going to say it's ideal. If it does have an impedance, we're just going to refer it to the secondary side. And so PT, we're going to classify this as a bus on the primary side of the transformer. ST is going to be the secondary side downstream, where we have this transmission line in the middle. And then we have this ST prime, which is going to be the virtual secondary side bus. And this is going to be on the secondary side of the ideal transformer. In a physical sense, we can say that this is actually attached to the primary side when we're doing our calculations, but we're going to treat it as its own bus. AT is going to be its turns ratio. Now, the work that we've done prior is we don't really want to deal with this model. And so we introduce a different one. And so rather than, this is what you would see in 476, where you have the admittance matrix that's going to be dependent on the tap ratio. And so what we do is we just kind of throw that out. And we say rather than model it in a circuit sense, we model it as input-output power. And so we introduce this extra term here that I call SPT, ST prime. And so, so this is great, but then we run into another problem that our graph here is actually disconnected. So when we do our semi-definite programming approach, there's this whole, and this is what my last presentation was on, is this whole like rank 1 issue, and this causes problems. So we add one more thing, we put a little resistor right there. And so consequently, this is going to be a large impedance, and this is going to get penalized naturally in the way that we set up our optimization problem. But still, what's important here is that we have that power, essentially the load on the primary side and the ejection on the secondary side. And so this is the model that we're going to be working with when we're determining transformer taps. And what's actually kind of neat about this is while we're doing our minimization problem, and on the next, I'm going to go into set theory, set notation. While we're actually doing our minimization problem, we can throw out our tap ratios altogether and then bring them back in once we have our solution. And so again, some more notation. We're just going to say transformers are T, primary sides NP. We have our secondary side, our virtual secondary side. And then we have the rest of the buses in the system. I say standard buses. And so our original system, that's actually the set of physical buses, is going to be this N here. And that's going to include just the standard buses, the primary and secondary side. But then we have this augmented network with those virtual secondary side buses. And so, again, some more set notation. We're going to track all the powers if we have multiple transformers. We're going to track all the tap ratios. For the reactive power support, we have a similar structure where we're tracking the reactive power that we can inject or consume. And then our admittance matrix and everything like that is actually going to be based on that augmented network, so it's a little bit different than maybe you would come up with in the original. And then we have this H, and this is just for completeness. This is the set of buses electrically connected to bus I. And so our general problem statement is going to be this minimization problem. We're going to have some cost function. Generally, this is always going to include some sort of losses, but then we can include other things in it, like voltage regulation. If Professor Sauer is here, he'd name all kinds of things. But our primary concern is going to be voltage regulation. And then we're going to have our power flow on our standard buses. Because I have that updated transformer model, we're going to have power flow on the primary side, the virtual secondary side. Now, note the secondary side just falls into the standard power flow in this case. And then also we have to concern the voltages on either side. And this is because I still have taps. And you'll see it on the next slide where I actually put this in a mathematical formulation. Then we have all our inequality constraints. This is how far up and down our taps can go. This is our reactive power, our voltage constraints. So mathematically, this is the exact same thing, the exact same layout. It's just I introduced all the notation I talked about earlier. And so this is regular power flow. This is just our standard power flow equation here. That's the power. This is actually reactive power support right there. The primary side could have reactive power support. Definitely the virtual secondary won't have it. These are our voltage limits that we have to concern. Yeah, the difference is this right here, because this is an optimization variable, whereas the regular powers are actually declared or constants. Yeah, that's the power through the transformer. So that's an optimization variable that we determine. And so through the magic of my last presentation, we go to this form. And like I said, this is where I'm skipping a lot of stuff for brevity. And so essentially what we did here is rather than deal with we have all these quadratic terms here. We reformulate it using what's called semi-definite programming. And that's actually really nice because now we have linear terms of everything. And so this is saying the same thing. I won't go into too much detail, but later on, it might make more sense when I start laying out the way the matrix looks.
Maybe you can tell them what W is.
So W is actually, it's the outer product of the voltages. And so a lot of times, if you look right here, you end up getting like a voltage times one of its neighbors, like a conjugate. You get all these squared terms. And so this will show up in the W. And I actually do declare W in a couple slides later that if you're paying attention, you might catch it. So this is, again, we have our cost function. This is just going to be standard power flow, primary, secondary side. The power through the transformer is going to be a decision variable. We're going to limit, because this is the outer product, so we're going to limit the diagonal entries of it because those are going to be the magnitude squareds. And then the only exception is that virtual secondary side doesn't actually, it's not constrained to specifications. It's constrained as a function of the primary side, so that one's a little bit different. This is not convex yet because that's our whole goal is to make it convex because we have this rank 1 constraint because we're dealing with an outer product. So we dropped that, and now it's convex. And so then we apply our convex solvers to this. Before I was doing centralized, now I'm going to do it distributedly. And so why do we want to do a distributed solver? Well, a common argument would say, oh, we have a simpler communication architecture compared to a centralized scheme because you really just need to know your area. The other thing is if we actually do solve this in a centralized way, this is nice because it reduces the complexity of the problem. And I have this statement here that the complexity scales with the size of the partition rather than the network size. So if you're doing it locally and you have a bunch of cores, you can actually set this up as a distributed problem and just solve it on one machine, and it'd be pretty quick that way as well. And so this is that outer product that Alejandro was mentioning here. So like, for example, you would have like V1 squared and then V1, V2 conjugate. And anybody familiar with power flow would recognize those terms. And so just to give you an idea why it scales with the partition. So suppose I have two partitions where I'm only worried about this upper part, and then I have another one on this lower part. And then we have to have these boundary conditions where there's some information overlap. And so we have that as W21, which is referenced towards relative to W2. Then we have W12 where we reference it the other way. And the savings are the fact that we have these white spaces. So these are variables we can just completely throw out. Now for small problems it doesn't really make a difference, but as we scale up you'll see it's a huge difference. Again, we have some more set notation because we have a lot of bookkeeping to take care of when we do a distributed approach because we want to make it so everything here is separable. And so I have this running example here of a 4-bus system. In this case, we're going to partition it into 2 areas, which are going to be buses 1 and 2 and buses 3 and 4. And then we have this extended area, which is going to be the neighbor of any bus that's on the boundary. So this has to do with the information associated with the power flow between buses 2 and 3. In order to keep track of your neighbors, we introduced this other set M. I lost the name of it for a second. And then Notationally, just to refer it back to that first slide, we have W1, W2, and then we have this W1, 2, W2, 1, which we want to be equal, but when we're solving it distributively, they won't start out as being equal. Now we run into a problem because this is not separable right now. Like we can't do local minimizations. So the way we handle this is we introduce these auxiliary variables E and F. Essentially, E is going to be the real part of that voltage product, and then F is going to be the imaginary part of it, because W is complex, you know. And actually, when we solve it, we take the complex problem and we split it out. And so, essentially, what we're going to have is these boundary conditions. And so when we do our local minimization, we're like, for example, in area 1, this W1, 2, we're going to relate it to our boundary condition, and then we'll have these update rules. So over time, this E and F will actually converge, and then consequently, our W1, 2 and our W2, 1 will be equal as well. And so just to give you an idea what this looks like, because I certainly understand when you just see a lot of math, it doesn't necessarily sink in. For that 4-bus system, naturally our cost function is going to split up because we're going to do this based on line losses. Then we're going to have our voltage on the slack bus, which is bus 1, and then we have our power flow on the other 2. I didn't include transformers, and the reason why is because it would add a lot more complication to this slide. But then the other thing is if the transmission line that contains a transformer lies on that boundary between the two areas. Earlier I said that that virtual secondary bus would actually essentially be the primary side, right? So it wouldn't make any sense physically to have a transformer where the primary side is in one area and the secondary side, the virtual secondary side is in another area. It just doesn't make sense altogether. So it's always going to fall within an area. And so that's why I don't actually need to even think about it when I'm splitting it up. These are going to be our voltage limits. Again, notice that these are squared, and that's because we're dealing with an outer product here. In terms of the way that W looks for this example, this is going to be our outer product. And then when we start looking at the areas like I did earlier, here's area 1, our extended area, area 2, our extended area. And then this is the overlap right there, and we can split it up. And you can see with this problem, we're only going to save 2 variables. So there's actually, this is an easy enough problem where we won't really want to apply this, but for large systems, it makes a pretty big difference. And so again, this is just the simplified notation here. Now we separate everything. Again, it's not separable yet because I haven't introduced these auxiliary variables. And so we make it separable by adding those auxiliary variables. And so just moving everything around and simplifying it, this is the way that we're actually going to, this is the notation for each area, the problem that we're solving. And so we're going to minimize our cost function relative to the W within this set B. And set B just captures all the power flow and inequality constraints that are just a given. And then we have our boundary conditions here. Just for completeness, this is how we define B for each area. You can see your slack, there's your inequality, and there's your power flow. And then generically for the entire system, we're going to sum over all these cost functions. Each area is going to have its own power flow constraints. We're going to have our boundary conditions. Technically, our boundary conditions have to be equal for, relative to its neighboring area. When we solve for it, we take advantage of this in the update rules, but it's not something we have to consider in the optimization. And so, for those of you that have had 490, this is going to be familiar. For those of you that haven't, I think you've probably seen something like this in calculus. And so we're going to minimize some cost function relative to this equality constraint. I say here that it's equality constraint convex optimization problem. And the way we solve this is because this is constrained, we introduce this Lagrangian right here where we essentially move our equality constraints up top into the objective function. We introduce this dual variable. And essentially this allows us to formulate the problem as an unconstrained problem. However, for our purposes, this isn't quite enough. We add one more thing to it, and we use what's called the augmented Lagrangian, where we add this penalty term. And the way this works is that when we initialize our problem, we're going to be way off because we have no idea where to start. And so when we're in that case, we're going to be penalized very heavily by this term right here. And as we get closer to our actual answer, this will decay off and our dual variables will take over. And those of you that have taken, 573, you understand that dual variables actually are very useful because they tell you many things actually. And so this constancy here is going to be called our penalty parameter. And so the approach that we're actually going to use to solve this is, typically you would formulate it and you would use what's called a dual ascent method. And we're going to be doing that. We're going to be using something that's called the alternating direction method of multipliers. And essentially the difference is if we look at that cost function, we divide it up relative to x and z. So you can see I no longer just have f of x, I have it's separable because I have this g of x. And similarly for the equality constraints. In ADMM, what we do is we do separate x and z minimization. So we minimize the Lagrangian relative to x, and then, well, it's actually an argument. And then we use that value, we plug it into z when we do the same thing for z, and then we do our dual ascent here. Now, excuse me, because we are using an augmented Lagrangian where we have this penalty term that I said on this penalty parameter, our step size is going to have to be that, and that just has to do with convergence. Now, the benefit, while this is the disadvantage, is that it takes a long time, depending on the size of the network, to get to converge to a high accuracy. However, it does converge to a modest accuracy fairly quickly. And that's okay because when you look at the results, the cost function is going to converge even though the taps haven't yet. And so there's like this gray area. There's like a number of taps that will give you a similar answer. And so as long as we're working with that, we're ahead. And so it's okay. To take that separable expression that I talked about earlier and create the augmented Lagrangian, you can see here I have the cost function. These are our boundary conditions, the dual variables associated with it, and then this is our penalty term that we add.
Maybe you want to tell them what is the F norm that you have there.
This is the Frobenius norm, and so this is a component-wise sum/square. And so what you would do is you would take entry 1, of both of these, square it. Well, so you're going to have a difference in entry 1 here. You're going to square it, and then you're just going to sum every entry. So that's all the Frobenius is. So it's like doing an L2 norm on a vector, only it's for the whole matrix. And then if you take this and you do your partial derivatives and everything like that, and then you take your updates and you plug it all in, so I saved a lot of math here, you get this right here. And so for each area, we're just going to solve the argmin of Lagrangian for W. This is where we take care of all the power flow constraints. That's why they don't show up in the Lagrangians, because we handle them here. And then when we take those results and we plug it into how we update the auxiliary variables, you can see we end up taking the average of the boundary conditions determined in each local optimization. And then we have our dual ascent update here, where we use the penalty parameter that we use from the augmented Lagrangian. So to give you an idea what this looks like, I started out with this 15-bus system. This is derived from the IEEE 13-bus system, where I just added a couple buses. Now there are, because it's 3-phase unbalanced, so there's a mixture of single, 2, and 3-phase. In this 15-bus system, there are actually 41 phases that we have to solve for. And so what I did is I split it into 2 areas. You can see the boundary is going to occur right here on 632 and 693. And so in the centralized scheme, we have 1,763. Now that kind of makes sense, because if you take 40 and you square it, knowing that we have 41 phases, we're already up to 1,600 variables. So you can see how it scales. It scales exponentially as we increase the number of buses or phases. Now, with just this layout I did with the areas, it dropped to 1,379, which is about a 22% reduction. The other thing is we do get the same solution for both the centralized and the distributed scheme. Here's some plots. We like plots, they're pictures. There's the taps right there. Now, the taps, I overlaid them with their discrete positions because, we did this assumption where they're continuous because it's much easier to do that because we don't have to do mixed integer programming. You can see there's always going to be a slight error unless we get really lucky and it falls right on a discrete value. But this is what I was talking about, where this is fairly flat here. This is going to be the cost functions. These are the cost function for each area, and the blue one's the sum of it, so that's the actual cost function that you would have in the centralized scheme. And then down here, these are the power. This is the power that gets transferred through the transformer, and that's our other auxiliary variable that I mentioned in the formulation earlier. And you can see that those go, they reach their steady state position pretty quick, where they're flat, but the taps are still moving. And that's why I was saying we don't actually need to sit there until we get the absolute optimal tap position to get the answer that we're looking for. And then right here, this is that penalty parameter from the augmented Lagrangian. And this is just showing you that as we vary that value, it changes how it converges. Because what happens is if it's too large, that extra term dominates it. If it's too small, then it still takes forever. So there's kind of a balance on where we put that. And I guess you would determine that through heuristics or just historical data. And then we scale up to a larger system. This is the 123 bus system. I got it in 6 areas. It's all color-coded. There are 259 phases that we have to solve for. The loads are mostly unbalanced. It's a mixture of overhead underground transmission lines with various phasing. We have 4 voltage regulators. One of them single phase. We have one that's 2-phase, and we have 2 3-phase regulators. Now, if you think about it, we have 259 phases. In this case, we have about 270,000 optimization variables. And the reason why that we have that is if you take 259 voltages that we have to solve for, it's complex. So now you have to double that. And so you're at like 500 and something, and then you square it, and now you're getting close to 200. It's like 268,000. Then we have to add in like complementary slackness and a bunch of other variables. So that's where we get the 270. But dividing into 6 areas, we drop it to 60,000. So there's a 78% reduction just by splitting it up in the areas. Now there's a trade-off because the more areas we have, the less variables we have to solve for. However, the longer it takes for the distributed solution to solve. So that's kind of interesting. The other thing, just to show you, the objective functions are nearly the same. I think it's like a 0.3% difference if you call it out. Right now I'm just minimizing losses, but in future work and what we're doing right now is we're adding voltage regulation. And so we do that by taking our original cost function, which is losses, and this is needed for our whole convex relaxation that we do, and we add a voltage regulation cost to it. And this could be you have a reference voltage that you're tracking, and you take the square of the voltage, the difference of the square of the voltages. And essentially what that does, and the reason why it still works, is because if you go back to my previous presentation, we love talking about these ellipses. And these ellipses essentially represent the power transfer through a transmission line. And so by varying the voltage, the area that we want a solution falls in this lower left-hand side here. And you can see I varied the voltage. This is if it's 1 per unit, and this is 0.8 per unit. So there's no reason why neighboring buses would have that big of a voltage variation. But that area that we're interested in, the solution right here, doesn't really change it. It all changes out here. So by adding that voltage regulation term, we're essentially penalizing the size of the ellipse, not actually the area that we want to have our solution in. And then this line right here, that's thermal limits. That's saying that we don't have some ridiculous phase difference across the transmission line. And then as far as what we're working on right now, is going back to my original slide, this is going to be the fast timescale control. So the slow timescale control is how do we set transformer taps and mechanical devices. The fast timescale is going to be mostly reactive power support. And so you can do that with some sort of feedback control, which we've done in previous work. The other thing we're actually working on right now is casting it as a minimization problem. And you can see the minimization problem is much simpler here, right? Because we have our decision variables. We're going to have voltages. We're going to have reactive power support. At this point, our taps are fixed, so we just work with the original admittance matrix where we have our tap ratios included in it. So it's much simpler. We don't have all these, the primary and secondary side and all these additional constraints associated with it. And then as far as concluding remarks, with the slow time scale, what we're working on is it works. We have a paper that's written on it, but we want to improve it. We want it to converge faster. Part of the way we do that is we know that power has to be going through a certain way on a boundary, so maybe we constrain that. So we're going to be doing that. We're going to be incorporating voltage regulation. I forgot an L there, one mistake. No, Alejandro keeps it less than 8. And then we got the fast time scale, which we can actually do using the semi-definite programming approach that I kind of talked about earlier, but didn't go into depth, and then also using our the feedback control that we've done in the past. But the other thing is we're exploring other possible ways to do this as well. And then once we have all of that, we're going to bring it together and do a complete timescale separation. where I'm going to start it at time 0 and I'm going to hit go for a week and feed in load data and solar panel data and PHEV data and kind of see how it works there and what lessons we learned from that. So, any questions? Okay.
Yeah, so with the long time scale optimization,
Yeah.
is your goal to choose the tap position?
Yeah, well, primarily the goal is to choose the tap positions right now, because we don't really want taps changing all the time, right? Because there's mechanical wear and tear. Now, keep in mind that the picture I drew it is very periodic, so we could maybe set tap positions on 15-minute intervals at the worst part of the day, not change them all at night.
Yeah.
We could also run the the slow time scale optimization and say, oh, our tap didn't change enough that's actually worth putting a new value in. And so
choosing that tap position though would be when you're choosing it for a particular loading of the system.
yes.
So could it be that at one loading of the system, you have one solution, and that's really great there.
Yeah.
But it's really horrible at a different loading of the system. So if you don't update in between, like change the system loading,
Yeah.
do that worse off overall.
Yeah. Well, when we are assigning the taps, we are tracking power. We can measure it. The other thing to keep in mind is that maybe the loading includes reactive power support, and this is something Alejandro and I were talking about today. Is when I assign the slow time scale control, maybe I set everything, and then I use the reactive power support to kind of maintain that for that 15-minute block, right? Yeah. Yeah, that could be variable because it doesn't make sense to run it every 15 minutes throughout the entire day. But maybe from 5 to 7 we do it 15 minutes. From midnight to 6 a.m. we just leave it alone.
I thought you were on the order of days.
No. It's yeah. Because typically what happens with the voltage regulator is you have a sensor on the secondary side and it goes, whoa, wait a second here. I don't like that. And it's been like that for like 30 seconds. That's not happening. And then it just starts moving all over the place. Yeah, they think like that. Because Pacific Northwest National Lab, they collaborate on this. They have Grid Lab D. You set all the constants. So, Catherine.
So I can understand a little bit better. So if they have a PV system,
Yeah.
model, is that a set variable, or is that just like the power?
So the way we're going to model PV when we do this time scale is we're not going to necessarily do it from a random process standpoint. I have a bunch of historical data that I can throw in there. And so I guess maybe the disadvantage with that, because it moves in discrete time increments, I think usually the load data is on the order of a minute or 5 minutes.
Yeah.
And so it doesn't necessarily capture the volatility of it. I guess that's not really so much the focus of my work is the random part, is more how to implement. Now that's something we could add in as we complicate things, right? Because you do something simple and then you make it harder. And then when you do that, you're like, oh, I got to make it harder again.
Have you guys ever thought about using curtailment? So like actually adding a signal back to the PV system to say like reduce your power? Would that incorporate into this at all?
Right now we're not looking at active power in terms of controlling it. We're just controlling the reactive power component of it. However, we do vary the active power, so that's something we could look at later on. And we could add it in the framework that I talked about where we did the convex relaxation if we really wanted to. It was just we'd have another inequality constraint rather than a constant.
How did you determine your number of areas? So you just gave that 6 areas.
Yes.
How did you
So the way I did that was I was like, well, how many areas do I want? 6 sounds good. And then I kind of just, I went over here and I just kind of, it was very much based on the structure of the graph. And the biggest thing I wanted to convey here was not that I was trying to pick the best area configuration, was the fact that if I had a lot of areas, there was a huge reduction in the number of variables. Now, one thing we talked about on a conference call is, well, is there a better way to pick this? And so that I'll just chop that off to future work. But yeah, good point.
Let's take that partitioning problem. And you may want to have some objective in terms of the partitioning. You want to maximize or minimize the partitions. And so, for example, right now, what is this? Oh, here. He's working on another problem of instrument detection in transmission networks, and again, he's looking at the algorithm to partition the network, and the optimality criteria is what was happening like the number of guidelines, or how they have counts. Right.
Future work, also referred to Shichen. Well, there's a joint paper right there. Any other questions? So I'm going to turn it over to the Bell's Pest guys for elections.